Now, we've looked at the various parts that make up a mapping. So we move on to operations on mappings. Here, we want to know how we would multiply two mappings together. So if we were in calculus, okay, there we're working with real valued functions. If I multiply two functions together, we're just going to multiply the values together, and we get another real number. Here, we're just working with general sets, so we may not be able to multiply values. There may not be a natural multiplication on a range space. To make something work, we're instead going to consider composition of mappings. Now, if we're treating our mappings as points to be multiplied together, we should be clear on when two mappings are the same. So when are they the same point? So if I have mappings f and g from set x to set y, when would they be the same? Well, we want them defined both on the same set of points, and for each of those points, we'll want our two functions to take the same values. So formally, I would say domain of f is equal to domain of g, and for all x in the domain of f, which is the same as domain of g, f of x is equal to g of x. For an example from pre-calculus, okay, I could take the function f of x from the real numbers back to themselves, given by x squared minus 1 divided by x minus 1. Now here we could cancel an x minus 1 out of the numerator and denominator, leaving us with an x plus 1. Now note, these two functions are not the same. Okay, this function here has 1 excluded from the domain. So if I wanted to line these up using our definition, I can use x plus 1, but I would have to say that x is not equal to 1. So 1's not in the domain. That makes these two functions equal. Now, if I want to multiply two functions together, things have to be set up correctly. So here's our definition. I'll have a mapping f going from x to y. We'll have another mapping g going from y to z. So how can we combine these two things together? Well, if I have some x and x, put it into f, point comes out of y, and then I can take that point, put it into g, it goes over, point from z comes out. So with this stringing together, which is what we're calling composition, I'm going to put something in for x, something from z is going to come out. Now note when we write this down, okay, because of the way we read functions, okay, we usually evaluate from right to left, I have to write this backwards. So the idea would be x is going to go into f, becomes a point of y, then that y goes into g. So I write it like this. This composition, okay, f and g, becomes g composed with f. Now, the way we define it is just as I said. We're going to put our x in for f, becomes a point for y, and then we can evaluate g at y. So we write this like this. Okay, pictures, we have something in x, send it over by f, and then send that over by g. Now, the reason we refer to composition as multiplication of mappings is because we can draw some parallels to multiplication of real numbers. For instance, we have associativity of composition. In the real numbers, this says, if we have a triple product, if I multiply the first two and then the third, get the same answer as if we took the last two and then multiply by the first. Okay, and note the orders of our labels are the same. It's just which pairs we pick first. For this to work with mappings, we have to make sure everything's lined up correctly. So we'll have mappings f, g, and h. F carries x to y, g carries y to z, h carries z to w. Now, to show that these two functions are the same, we just show that they agree for each point x in the domain. So we'll take an x. What's the rule say? Well, we're going to take our x, put it in the function on the right, then take f of x and put that in the function on the left. So here we'll have h composed of g, evaluated f of x. Then I apply the rule again. So I'll put f of x into g, and then we take that, put it into h to give us this term here. If we use the other pair, we apply our rule. I stick x into g composed with f, then we stick that into h. Now to evaluate the inside term, I'm going to put x into f and then put that into g. So we'll get the same term that we have here. The values are the same, so these are the same function. So associativity. Now, seems like all we did here was symbol pushing, but this is a perfectly valid proof of this statement. Also, okay, associativity, we tend to take for granted. Okay, most things that we use in math are going to be associative, but just remember, not everything's associative. For instance, subtraction. Now, another item, we have a multiplicative identity in the real numbers. So it's going to be the number 1. Anything I multiply by 1 gives me that number back. So when we talk about mappings, for the identity, we can use identity mappings on a given set. So if we have the set x, the identity mapping is just going to carry x back to itself. If we take any y and x, the identity map just sends it back to y. So it really just says do nothing. Now, if I have a map f carries x to y, we take f composed with the identity map on x. It's just going to give us f back. So let's check that. So our rule says take x, put that into the identity map on x, and then stick that into f. Well, the identity map is just going to give us x back, so we get f of x. And we have that these two functions agree for every x, so they're equal. So I have this statement. Likewise, if I take the identity map on y composed with f, we get f back. It's going to be the same type of argument. Okay, note here, this f of x is going to be an element in y, so it makes sense to put that into the identity map on y. Now, each non-zero real number has a multiplicative inverse. So if we take non-zero x, we can multiply it by 1 over x, and then we get 1, the multiplicative identity. We want an analog of that for composition of mappings. So what we're looking for, if I have f carrying x to y, I want an f inverse, okay, with a -1 up here, carrying y to x, such that f inverse composed with f gives us the identity map on x, f composed with f inverse gives us the identity map on y. If we could find an f inverse that does this, we'll call f inverse the inverse function for f. Now, let's assume it exists, and then we'll see how we have to define it, and then we'll try to draw properties from f that guarantees its existence. Now, if we have f of x equal to y, well, if I put x into the first equation, okay, I have f inverse composed of f on x is equal to the identity map on x. If we collapse this, so I'm going to put x into f and then put that into f inverse. Okay, I know f of x is equal to y, so I get the equation, if f of x is equal to y, f inverse of y is equal to x. So the way I go from f to f inverse is just to switch the order of x and y. Now, we're defining our function f as a subset of the Cartesian product x cross y. Okay, the rule is we just send x comma y to y comma x in the Cartesian product of y with x. Now, noting that if we have that f inverse is a function from y to x, okay, recall the property we have here. If we have that y comma x and y comma z is in f inverse, we have to have the x is equal to z. So our function's single valued. Now, if we unravel this for a condition on f, what's that say? Well, that says if x comma y and z comma y are in f, then we have to have the x is equal to z. Now, this first part just says f of x is equal to f of z. And the way we read this, that's the definition for f to be 1, 1. So that's the first condition that I need to have an inverse function. On the other hand, if I want f inverse to be defined on each y and y, okay, we want the domain to be all of y, well, that's going to mean there's going to have to be some x and x such that f of x is equal to y. Then I can define f inverse as f inverse of y equals x. That means that we have to have the f is onto. To summarize, if we have a mapping f carrying x to y, then inverse mapping or inverse function of f, okay, we call that f inverse, from y to x exists if and only if f is 1-to-1 and onto. If that's the case, we define the inverse map, f inverse of y equals x, whenever f of x is equal to y. So we just switch x and y. Finally, we have that if we compose f inverse with f, we get the identity map on x. If we compose f with f inverse, we have the identity map on y. Now, for an example from pre-calculus, consider f from the real numbers back into themselves. Consider a function which has this graph of line, f of x equal to 3x plus 4. We've already seen that this is 1-to-1 and onto, so it has an inverse function. Note, if I want the equation of the inverse function, okay, we're carrying points x comma y to y comma x, so we want to solve for x, meaning we isolate the x. Now if I do that in this equation, we get x equals y minus 4 over 3, which is f inverse of y. To check, we take the composition of f with f inverse, okay, evaluated at y. So we're going to have y minus 4 over 3, put that into f, and we get y out, which is the identity map of y on the point y. So that checks. Finally, if we're interested in the graph, well, we're taking points on the graph of the form x comma y. Our rule is to switch. So for the graph of the inverse function, we're going to plot y comma x, which is the same as flipping through the line y equals x. Okay, and that's going to be at a 45-degree angle. So we're going to carry this line here to this one here. If you need guide points to see where things go, for instance, I could take 0, 4 and minus 1, 1, okay, which are on the original line. We switch the x and the y to get new points. So 0, 4 goes to 4, 0, minus 1, 1 goes to 1, minus 1. For some simpler examples, let's consider x equal to y to be the set 1, 2, 3. So for the identity map, we have 1 goes to 1, 2 goes to 2, 3 goes to 3. If I consider f as the map 1 goes to 1, 2 goes to 1, 3 goes to 2. Since I have both 1 and 2 going to 1, this map is not 1-to-1. So the inverse map does not exist. On the other hand, if I take f with 1 going to 2, 2 goes to 3, 3 goes to 1, this is 1-to-1 and onto. So this is going to have an inverse map. Now how do we get that inverse map? Well, if our points are x comma y, for the inverse, they're going to be y comma x. So that just says to read this backwards. So I'll have that 2 goes to 1, 3 goes to 2, 1 goes to 3. And then you just can rearrange these so that we have 1, 2, 3 in order on the left-hand side. Of course, we could check this. So if I take f composed with f inverse, okay, what do? We do f inverse first. So 2 goes to 1, 1 goes to 2, so 2 goes to 2. 3 goes to 2, 2 goes to 3, so 3 goes to 3. And 1 goes to 3, 3 goes to 1, so 1 goes to 1. And we have the identity map when we compose. Some more results on the inverse function. Okay, we have f carrying x to y. If the inverse function, f inverse exists, we have also that f inverse is 1-to-1 and onto. So it has an inverse function. Its inverse function is just f itself. So let's check this. For 1-to-1, okay, I'll assume the f inverse is going to have the same value on y and y prime. So I want to show that y and y prime are equal. Now, for the last two rules in the theorem, okay, we call those cancellation rules. If I want to take this f inverse off of the y's, I'll just apply f to both of these. Then f composed of f inverse is the identity. So it's the same as removing each of these. Okay, so we apply f. They turn into identity maps, and I'm left with y equal to y prime. For onto, okay, we're going to have f inverse carries y to x. So I want to show that we hit every point x in the set x under f inverse. So if I fix an x in our set x, if I apply f to this, we have f of x equal to y. So what I can do here is apply f inverse to both sides, okay, similar to what we did here. Then what I'll have is f inverse of y. That's going to be equal to f inverse of f of x. These cancel, leaving us with an x. So x is going to be in the range of f inverse. So we have onto. For the final property, okay, this is a little bit of a tongue twister. What would I do? Well, if I just unravel the definitions, if we have f of x equal to y, okay, for the inverse function we switch. So I have f inverse of y equal to x. Now, we know the inverse function exists by what we just showed, 1 and 1 and onto. So if I want to define f inverse inverse, I'm going to switch again. So I'll have f inverse inverse of x is equal to y. And then we know that f, okay, where's that? That's right here. And f inverse inverse have the same value applied to x. So these two functions are equal. Now, the property of having an inverse function is important enough that we give it its own name. So definition, the mapping f carrying x to y is 1 to 1 and onto, then we'll say that f is a 1-to-1 correspondence between x and y. We also call it a bijection. The way we should think of this, so not only does f have an inverse function, but qualitatively, x and y are the same set, just with different labels. So what's happening here? We have our set x, so it's going to be a set of points with x labels. The 1-to-1 correspondence sends each of the points over, but now they're going to pick up y labels. Okay, so there's no doubling up of the x labels as we push them over, okay, 1 to 1, and we're not going to miss any of the y labels, so onto. Now, for a simple example, let's consider the sets 1, 2, 3 in ABC. I'll have 1-to-1 correspondence f given by sending 1 to A, 2 to B, 3 to C. So this is 1-to-1 onto. What this says, okay, now sets don't have a lot of structure, so we're just saying here that this set with 3 elements is essentially the same as this set with 3 elements. For an example where something's not working, let's try 1 goes to A, 2 goes to A, 3 goes to B. So we're sending the set 1, 2, 3 to the set AB. This is not a 1-to-1 correspondence because it's not 1-to-1. So 1 and 2 both go to A. And we expect that we should never have a 1-to-1 correspondence here, because otherwise it would say that a set with 3 points is the same as a set with 2 points. Okay, no matter how we relabel, we're never going to get those sets the same. We'll pursue this idea more in the next talk. Now, for some cleanup, if I take a composition of 1-to-1 correspondences, then I get another 1-to-1 correspondence. So to see that, we just want to see that the composition of 2 1-to-1 maps is 1 to 1. Composition of 2 onto maps is onto. Okay, so let's assume we have our f going from x to y, g goes from y to z. First, let's assume that f and g are 1 to 1. Okay, so we're just going to check our property, which will be that g composed with f on some x is equal to g composed with f on some x prime. And then I want to show that x is equal to x prime. So the composition will be 1 to 1. Now, if we just compute these by the definition, I put x into f, then put that into g. Okay, same for the other one. Because g is 1 to 1, the things on the inside have to be equal. So that says that f of x is equal to f of x prime. But because f is 1 to 1, we have to have the x is equal to x prime. So the composition is 1 to 1. For onto, same idea. So we'll assume that f and g are onto. I'm going to pick some z in z. Okay, that's where everything winds up if I take g composed with f. I want to show that I can find an x that lands on z. Now, because g is onto, we can find a y in y such that g of y is equal to z. Because f is onto, I can find an x such that f of x is equal to that y. Now, if we take G composed with F on that X, what do we get? I have G on F of X, which is G of Y, and then G of Y is equal to Z. So that means the composition is onto. Putting them together, that says G composed with F will be a one-to-one correspondence if F and G are. We've just seen that some mappings have multiplicative inverses, some don't. So the parallel to the real numbers doesn't quite work. Another one that doesn't quite work, commutativity. So in the real numbers, the order of multiplication doesn't matter. We take x times y, it's always equal to y times x. Now, this is going to fail in general for composition. So if we have f carrying x to y, g carrying y to z, g composed with f is going to carry x to z. F composed with g usually is not going to be defined. Okay, it'll be defined if x and z are the same set. Okay, so note g is going to carry y to z, f is going to carry x to y, and somehow we've got to get things in the middle to line up. Now, even if we had x, y, z all lining up correctly, we still might not have this commutativity. So for instance, if we just take, okay, our x equal to y equal to z, this is set 1, 2, 3. I'll have f carrying 1 to 2, 2 to 3, 3 to 1. G carries 1 to 2, 2 to 1, and 3 to 3. If we work out the compositions, so G composed with F, okay, so that says do F first, since it's on the inside. We have 1 goes to 2, 2 goes to 3, 3 goes to 1. Then I'll have with G, 1 goes to 2, 2 goes to 1, and 3 goes to 3. So our composition is just to read the last column. If we go in the other direction, okay, now we're doing G first. So we'll have 2, 1, 3. Then when we apply F, we have 2 goes to 3, 1 goes to 2, 3 goes to 1. Our last columns are not equal, so these compositions are not the same. So switching the order doesn't guarantee that you get the same result.